Right, tunneling. So last time we looked, in the last video, we looked at the potential steps. So our energy landscape was a simple step in the potential. Now we're going to look at a barrier. So a potential function looks like this, which is like a little hill. Rather artificial square hill, but a hill or a barrier in potential, where it's A wide, and we can define it as Vx is equal to 0, x less than 0, Vx is equal to, let's put it this side, V0 for x greater than or equal to 0 and less than A, and Vx is back to 0 on the other side, so x greater than or equal to A. And we're going to consider this case where the energy of our particles, E, is less than the height of that barrier. Again, classically, they just get reflected. Quantum mechanically, the difference between this and the potential step is that for the potential step, we saw that there wasn't a flux. There was an exponentially decaying probability density, but there wasn't a current that was transmitted. Here, there is a flux that makes it through, as it were, the other side of the tunnel barrier. And that, as I've said before, that tunneling process is absolutely key. The fact that the particles classically don't have enough energy to surmount this barrier. Quantum mechanically, they tunnel through the barrier. It's important to think that they're not. It's important to realize that it's not a question of jumping over. It's a question of this energy being conserved as it goes through. We call this elastic tunneling because the energy is conserved. So the algebra gets a little bit involved in this one. Again, I'm not going to laboriously go through every single step of the algebra. You are more than capable of doing this algebra for yourself. It's not beyond, in terms of the algebra, it's not beyond anything you've done at A level. So I'm going to give you the results. I'm going to ask you to step through this, make sure you just double check the results I'm going to show you, go through the algebra for yourself, and I'll tell you how to get to that algebra. But this is our system. And this tunneling process, as I've mentioned before, is so key, so central to so many aspects of physics. And later on in this video, we're going to see it exploited in the scanning tunneling microscope, which allows us to image individual atoms and to explore atomic landscapes and quantum landscapes, etc. Right, what we have, so wave function, we'll divide this into three regions. This is region 1, this is region 2 in terms of the barrier itself, and this is region 3. Got an incoming flux, an outgoing flux, just as we had with the potential step, because in terms of at this point, this is a potential step. Then we've got solutions to Schrodinger's equation, which give us wave functions which don't have, which aren't complex exponentials. They're exponential functions with real exponents. We'll get to that in a second. And then out this side, we've got a flux again. So we've got a current through. We've got a tunnel current, probability current, flux, whatever you want to call it. We've got a flux through this barrier. And the flux out this side, the probability of getting a current of particles out this side depends critically, exponentially on this width. And it also depends on the difference, as we'll see, between E and V0. So we can write down our wave functions in regions 1, 2, and 3 as follows. Region 1 is A e to the I k1x plus B e to the minus I k1x, just as we had for the potential step. So because we've now got a barrier rather than a step, a wave function in this region is going to be C e to, we've got to, for the complete solution, we've got e to the k2x plus de to the minus k2x. So instead of having a step, now we've got a barrier, which means we can't rule this term out. And in this, we're back to or potential being 0, so that means that we can use the same wave number in this region again. Now we could call this K3, but K3 is just equal to K1 because the potential here is 0 and the potential here is 0. Okay, and what I haven't done here, don't get confused, I haven't added in the little prime that I had in terms of the potential step. We can just go ahead and just write this as K2, where let me define what K1 and K2 are. So K1 is exactly as we had for the potential step, 2me over h bar, and K2, we're just going to go ahead and do it in that form. The reason I used that K2 prime in the last video was really to put across that idea of a wave number and therefore an exponentially decaying term rather than an oscillatory term. But let's go ahead, let's put down in some of the, just go ahead and call that K2. Don't get confused by that. Notice how I've defined K2 in this case. Right, so those are our wave functions. Those are our values of K. We're going to determine, or you're going to determine, transmission and reflection coefficients. But before we do that, let's look at the probability density. So let's call that A. So we've got our region here. This is region 1. This is region 2. This is region 3. So, and what we're looking at here is the probability density. So, as we had before, well, first of all, we've got an exponentially decaying term in here. And we've got some finite flux. And because it's e to the ik1x here, it's exactly the case as we had for the potential step when the energy was greater than the step. So, in the barrier region, we've got some exponential decay off. And then this side, we've got exactly what we had before in terms of a cosine-like dependence, because we've got wave coming in, reflected wave, and the combination of those two gives us this cosine-like dependence and a probability density. Exponential decay. Okay, so that's our wave function. Those are our spatial frequencies, our wave numbers. Now let's think about the transmission and reflection coefficients. Now, I'm not going to step by step take you through the algebra, as I said, but I will give you the key ideas. Again, it's about matching the wave functions. In this case, we're going to match them here, but we're also going to match them at x equal to a. So we're matching the wave functions, and we're also matching the first derivative of the wave functions. Okay, so usually I put the notes to one side and I talk through as I'm doing the algebra. I'm actually going to pick the notes up because I don't carry these particular equations around in my head. So if we're going to match the wave function and its first derivative both at x equal to 0 and at x equal to a. So if we do it at x equal to 0 in terms of the wave function itself, we end up with... Oh, the other thing I'll just mention, and apologies if I mentioned this before, but it's worth stressing again. Although we're breaking up the wave function into these different regions and we're considering the wave function in these different regions, it isn't that there are 3 separate wave functions as such. We're considering the behavior of the wave function in these different regions, but this is one continuous function. Very important to realize that this is one continuous wave function. Although we're breaking it up into different regions, obviously to extract the parameters we need, it's important to think of the wave function as one continuous wave function throughout. But if we match the wave function, which is why we do this matching condition. So if we match here and here, here's if we match the wave function. If we match the first derivative, what we're going to get is this, ik1 a minus b equals k2 c minus d. You can hopefully see where this comes from. Taking the first derivative, it's oscillatory here, so we've got a complex exponential, or exponent is complex, hence we get the I coming out. But in this region, our exponent is real, so we're just getting k2 and there's no I. Now we match here at x equal to a, and we end up with, in terms of the wave function itself, and its first derivative. I k1 e to the I k1a. Hopefully you can see all that, yeah. So I worked through the various steps in the notes. Page 87, so well, I guess best to refer to section 5.4.1, transmission and reflection coefficients for potential barrier. I worked through it, take you through those steps. Make sure you can follow through those steps. But one thing I won't be doing, so just get this out of your head straight away, there won't be an exam question which is derive the transmission and reflection coefficients for the potential barrier. It's important that you just step through this for the algebra and understand where this algebra is coming from. But, you know, in an online world, and even in an un-online world, even in a sort of real world examination where you don't have a computer to hand, just asking you to reproduce or regurgitate this is not a particularly good test of your understanding. It's a test of your ability to do the algebra. But if we churn through, and it really is a question of churning through all the algebra, what we get in the end is that our transmission coefficient, which is e squared over a squared, is given by, okay, bit of a mouthful this, 1 plus a quarter to k1 squared plus k2 squared over k1 k2 squared, and then there's a sinh hyperbolic function, sinh, not a sine, a sinh, k2a, and then all of that is to minus 1. So this is equation 543 in the notes. Right, where that's meant to be, I don't know why that says minus 2, that's meant to be squared. Okay. k1 squared plus k2 squared over k1 k2 square, all squared. Right. Sinh is interesting because it's hyperbolic function, so e to the x plus e to the minus x over 2. Given that we've got real exponents for in the exponential functions for the wave function in the barrier region itself, the fact that the hyperbolic function drops out, or hyperbolic functions like sinh and cosh drop out or appear in the final transmission coefficient and final solutions for the transmission coefficient, it's perhaps not so surprising. You'd expect that, given that we've got exponential functions with real exponents. Okay, so that's our t. That's our transmission coefficient. So you'll say, yeah, and so what? Well, let's, as all good physicists do, let's look at this in the appropriate limit. So let's just remind ourselves of what k1 and k2 actually are. I'll get rid of this now. Those are our k1s and k2s. So, a couple of things, couple of parameters we're very interested in from a sort of experimental perspective and from comparison with real world measurements. We're interested in the relationship of the energy of the tunneling particles against the height of the barrier. And sometimes this is called an apparent barrier height. I'm not going to use that term, it gets a little bit confusing. But this difference between the barrier height and the energy of the tunneling particles is one key parameter. And the other parameter, of course, is the width of the tunnel barrier. So let's think about getting that equation for a transmission coefficient, because ultimately what we're interested in is just how many particles make it through the barrier. What's the flux of particles that makes it through the barrier? What's the transmission through the barrier as a function of the difference between the potential barrier height and the energy of the particles, and as a function of the barrier width. So let's take our transmission coefficient and recouch it in those terms. Okay, so we've reduced the transmission coefficient to this term, or this form, where we've got two key parameters. Epsilon, which is telling us about the relationship of the energy of the tunneling particles to the height of the barrier. And also this term, which is counted in terms of the width of our barrier region. So it's an exponential decay of our wave function. So as we increase the barrier width, we'd expect our transmission to drop off exponentially with the width of the barrier. And we're going to see that that isn't the case. When we run some simulation soon, and we'll see that. We'll also see that is the case when it comes to the experiment too. So we have this exponential dependence on the barrier width. So if we've got that and got that, let's consider in the limit where E is much less than V0. So this will be much less than 1, and this lambda into 1 minus epsilon will be much greater than 1. So that means that given that sinh x is equal to e to the x plus e to the minus x over 2, and if this term is much greater, if the argument to the sinh function is much greater than 1, then this term's going to dominate, and this one's going to drop away. Okay, taking that into account, and also taking into account that epsilon is, if epsilon is much less than 1, then this term is going to dominate over the 1 here. So what we're going to have then is 1, because that term's dominating over the 1. Okay, and then when it comes to this term, what we can do is we can take our sinh squared, and we can consider it in the limit where this argument is much greater than 1, then we're going to just be left with this. This is going to drop out because if the argument's much greater than 1, then e to the minus something much greater than 1 is going to be very small, but this is going to be very large, so this term's going to dominate. So what we then have is we can take our sinh squared function, and that would be a half e to what our argument is here is, and then remember that's squared, and then this entire thing goes to minus 1. So now we've got we've reduced the transmission coefficient further in the limit. Remember, this is in the limit where e is much less than V0, so our tunneling particles have an energy much lower than the barrier height. Okay, what I'm going to do now is take that expression. We're going to have, squaring this term up, we're going to have 1 over 4 here. Take that out, then we'll have 1 over 16 epsilon into 1 minus epsilon. And then we're going to have, remember this is squared, we're going to have e to the 2 lambda root 1 minus epsilon. And then we've got to flip that round, we've got to invert that. So if we do all that, so remind ourselves of what epsilon is, which is that, what lambda is. Let's plug those into there, and what we're going to get is a transmission coefficient is 16e over V0 into 1 minus e over V0 into e to the minus 2, and lambda is this, a 2 m V0 over h bar squared into root 1 minus e over V0. So we're going to reduce that even further. Let me move this up the board again. Right, finally, that is the expression for the transmission coefficient in the limit where the tunneling electrons have a energy much less than the barrier height. We get this exponential dependence in terms of the barrier width, and also, as you might expect, we've also got this dependence on the relationship between the barrier height and the energy. There's a lot of work. I am not expecting, as I said, I'm not going to set an exam question which is derive all this and determine that. It's worthwhile you going through that algebra just to see that everything is consistent and all pops out. But what we were really driving at is to get this exponential dependence on barrier width out, because that exponential dependence is what gives the scanning tunneling microscope its incredible resolution, because the tunnel current or signal that we measure in the experiment is exponentially dependent on the distance between the tip and the sample, i.e. the barrier width. And so if we move the tip back just a fraction of an atomic diameter, it makes a huge difference to the tunnel current we measure, the tunnel current transmission, and therefore the flow of electrons, therefore the current of electrons, the tunneling particles in this case, depends exponentially on that barrier width. And it's that exponential dependence that gives us that super high resolution. That exponential dependence is also critical when it comes to electronic devices, when it comes to nuclear processes, when it comes to everywhere the tunneling plays a role in nature. That exponential dependence is very, very important. Okay, that was for, we've always considered this in the context of a flux of particles, which we've defined in terms of a plane wave a to the ikx. But we know that in reality, particles are not given by pure plane waves. We can think of a flux of particles, and we can model it if we're interested in one energy, but we don't have that perfect energy in reality. A wave function for a particle is much better described by a wave packet. That's a much better representation of reality. So let's look at the tunneling of a Gaussian wave packet.